Hi, today we will generate a bone fracture detection model. So this will be our test image, and we are going to find and detect the bone fracture in this image. And this model will be based on transformers. So let's start with creating our Conda environment. As always, I will leave a link to the code and for the instruction as well. So this install.txt files includes all the relevant command to create this Conda environment. As you can see, it will be based on Python 3.9. So let's create our Conda environment. Let's run the command. Let's call it Detr3. This will be the name of our environment. Let's run it. Great, it's about to finish. And now let's activate our new environment. As you can see, this is our current environment, Detr3. Now we have to install the PyTorch. So we will run the nbcc ---- version. As you can see, I have CUDA 11.8, so I have to look for the relevant PyTorch version that's suitable for my CUDA version. As you can see, PyTorch 2.3 is a good version, and also 2.2.2 is also suitable for my CUDA version. If you go down to previous version, as you can see, there are a lot of CUDA supported version. I decided to install 2.2.2. So let's run the command. Let's wait a few more seconds and it's done. Next, we should install Supervision. Basically, I will leave all the process in a fast forward process, so you can compare it to your installation. And as promised, I will leave a link in the video description to this installation file. So let's wait a few more seconds. Finally, in your IDE, I'm using VS Code. You have to change your interpreter to our new Conda environment that support Detr. Next process, we will create a new Python file, and this Python file will be dealing with all the data preparation. So let's call it step number 1, Detr, load the data. So we start by importing our necessary libraries: Torch, Supervision, Transformance, PyTorch Lightning, torchvision. This will help us and handle our deep learning and all the model architecture, training, file operation, and image processing respectively. Okay, next let's download our dataset. So let's open our web browser. As you can see here in the RoboFlow website, we can see there is a link here for a bone fracture computer vision project. So basically, here is information about this project. We can click here for look at the images. We have 458 images. Let's open one of the images, for example, this one. And as you can see, it's a X-ray image, and the fracture was annotated with these bounding boxes. So this is another image, and this is another image. You can see here is the bounding box, here is the annotation for the fracture, and this is another one, and this is another one. So basically, if we click here in the overview, there is a download dataset button. You can click this button, close this window, and you should choose this category, Coco JSON. And here you should download it download the zip to your computer, and you can see here it will split the data for 326 images for train, 88 for validation, and 44 for test images. If you click here continue, basically you start to download the images, and you will find it on your local machine. I already opened the zip file, and let's see, you can see it here. We have all the train images, and this is the JSON file with all the metadata and the information about the annotation for each of those images. We can open here the JSON file, and the JSON file contains all the metadata for each of the images. You can see here this is, for example, the ID for each image, the file name of each image, the height and the width, and we can go here and we also can see all the bounded boxes and the category ID for each box. And you can see here is another one and another one, so you can collect all the information about those images, and we will use it for our training. As for the classes, you can find it here in the RoboFlow dataset, and it indicates the type of fracture in the bones. I will leave here a link for all the relevant data sources. So this is the link for the dataset. So we will be able to download the dataset. Don't forget that you should download it with a COCO format. Next, we will set up our dataset path. We will specify the main folder and the defining path for our train, validation, and test directories. And also we will set the path for our annotation file name. Don't forget, we have an annotation file for the train and for the validation as well. So this part is creating and generating all these relevant paths. Okay, the next part is we will define our custom COCO detection class. This will extend the torchvision COCO detection and adapt it for our use case. So it will help us processing our images and annotations to be compatible with our transformer model. The next phase, we will create 3 data objects, one for the train, validation, and for the testing. So in order to do that, we will import the Detr image processor, and now we will create our dataset object using this Detr image processor, and we will specify the Facebook/Detr ResNet 50 as our prime model, and we will make basically 3 dataset objects, one each for the training, validation, and testing. And after that, we will print out the number of images in each dataset to confirm that everything was loaded correctly. Let's run it. Let's see the output. As you can see, we have 326 train images, 88 validation, and 44 test images. And the next process will be visual our images, but basically we would like to visual only one image. We will select a random image from the train set. So in order to do that, we will import the necessary libraries and choose a random image ID, and then load the image and its annotations. Let's print the image ID. And let's run it. As you can see, this random image is number 255. Let's run it again. Now it's 267. So basically it works. Now let's display our image. So basically we need to load the image and its annotation. So we will process our annotation and categories. We will create a dictionary mapping the category IDs to their names for the labels, and create a list of labels for our detected objects. Let's create the full path for our image, for our chosen random image. Now we will use the OpenCV library in order to load this image. And finally, we will use the Supervision library to draw a bounding boxes and labels on our image and display the annotated image using OpenCV. This will give us a visual confirmation that our data is loaded correctly and our annotation makes sense. Let's also print the categories. We have to fix this syntax error, okay? And I believe we are ready to run it. Okay, these are the list of the categories. Now let's run through the categories and create this label list. Okay, after creating our label list, let's display it. So now we have the categories and also all the labels. Great. So let's run it again. So now we have the list of the categories and also all the labels next to it. Perfect. So now let's display our image along with the annotations. So let's create an object for box annotation and let's run it using our image. So basically we will get a final image that contains all the bounding boxes along with the image. Let's run it. Great, as you can see, here is the fracture from our train image. Let's run it again, so we'll have a random image, another one. So this one has a different fracture named line. Let's run it again for a random image, another random image, and this one has a hand with a category of fracture. Great. So now we are ready to build our model. So let's start. We will be working with our bone fracture dataset and using the Detr transform model. Let's create a new Python file named train the model. And basically we need to copy some of the code from our previous Python file, so we will reuse it. All the dataset creation is relevant for our training as well. So now we have to deal with the data preparation. So let's define the function called collect_fn. This function is crucial for processing our batches before they pass to the model. It handles the paddings of images to ensure they're all the same size and properly formats our labels. Next, we set up our data loaders using PyTorch data loader, which will efficiently batch and shuffle our data during training. And we will also print out our category information to understand our classification targets. Basically, we did a similar process in our previous code. So we would like to print our categories and our labels after this step. Let's run it. So here are the categories and the labels. As you can see, we have 5 labels. Now let's create our train data loader. We are using the data loader function and sending several arguments like the train dataset, our collect function, batch size 4, that means how many images will be in each batch, and shuffling through, that is relevant for the train data. It's of course not relevant for the validation data. So we are creating a train loader and a validation loader. Next phase is creating our training object. We will use the PyTorch Lightning library in order to create this object, and we will import the Detr object detection class, and also we will use Hugging Face transformer library in order to import our model. So basically this will be our main class for the training process. So let's create our class. It will be named Detr and it will include several functions. The first function, the init method, initialize our model, loading our pre-trained Detr model and adapting it to our number of classes. In order to download it from the Hugging Face transformer library, we have to create a checkpoint variable named Facebook/DETR-ResNet50 and define it for our init function. Also, we have to define the number of labels. I believe it's 5 labels. Next, we have to define another method. We will call it forward, and it will deal with the forward pass of our model. So this forward method defines the forward pass for our model, and we will use it in the next phase during the training. I noticed there is a syntax in the word forward. I will fix it later. So the next step is creating another method for the loss calculation. So we will create a method named common_step, and it will compute the loss for both the training and the validation. Now we have to generate two methods, and the one would be training step, and the next one would be validation steps. And these methods handle the training and the validation process, including the logging of the metrics. We have to create another method. We will name it configure optimizers, and this method will set up our optimizer using different learning rates for the backbone and the rest of our model. Okay, next we'll define the function for loading the train data. Let's call it train loader. And let's also generate another function for loading the validation data. Now let's generate our model object, and we will also specify our learning rates and the weights decay. And after that, let's fix some syntax error, like the name of the forward function. And I saw another one. We have to fix this function as well. Great. And let's change it to forward. Great. Okay, let's continue. So now we are ready to train our model. So we will set up our PyTorch Lightning trainer. Let's define a folder for all the logging process during the training. And next, let's define the number of epochs. I believe we will run the model on 200 epochs. And now let's create our trainer. It will be based on the PyTorch Lightning. This trainer will handle the entire training process. So we will send all the relevant arguments, like the number of GPU, how many epochs, and all the gradient clapping, and the login, of course, and the fit function basically run all the training process. Let's also create a saved folder for all the calculated weights, and we will store it on this folder. Basically it's on an E drive, but I decided after running the training to change it to my home directory to C drive, just for performance. But as for now, you can choose your own local folder. So let's fix some issues on the syntax, like labels. It of course should be labels, and the model should be model.model.save pretrain. So let's run the model and see the training process. So the training has started. As you can see, this is the first epoch number 0, and you can see that it about to finish the first epoch. More than 50% has been finished. And now let's go for the next epoch number 1. So basically let's run it on a fast forward process, and we will run directly, let's jump directly to the final epoch, and let's see the results of this training. Okay, so finally, after about 4 hours and 5 minutes, the training has finished. As you can see, we ran about 200 epochs, and let's see now the results. First of all, let's go for the local folders. The model was saved here in this path. As you can see, this is the saved model. Also, all the config parameters are stored here, and here are all the weights are stored in this file, and also we can see all the log is stored here on this file in this folder, my DTR log, and inside there are several subfolders. And as you can see, this file metrics CVS, if we will open this file, you can see for each of the epochs and the sub steps, you can see the terrain loss. Basically, we are expecting that the terrain loss will go down for each of those 200 epochs. So after finish the training, we will continue to the next step, which is test our model. So in this section, we will focus on loading our trained model and uses it for our inference. So let's create a new Python file. Let's name it step number 3. And we will start with copying some of our code from our previous Python program. Let's copy until here, until the val validation loader. Now let's also copy the path for our model from our previous code. And the device would be CUDA. Let's also copy more of the import, the relevant import for our model. And let's use the DETR for object detection. And let's run a function named from pre-trained. So this will load our pre-saved model from our previous process, and let's print the model. We are expecting to see all the layers of all the architecture of our model. Great. So now let's move to the inference part. We will set up a box annotator from the Supervision library, and this will help us to use and draw our predictions on the image, on our test image. Next, let's choose one of the test images. We will load the test images from our dataset. Let's choose that one. So we will copy the full path for this image. Okay, this is the location and the name of the image. Don't forget to change the direction of the slashes. And we will use the IMRead in order to display our image. Let's import OpenCV. And let's use the IMShow in order to display our image, and the wait key for key press, waiting for a key press after we display the image. Great, so this is our test image, and we would like to find the fracture on this image. Next, let's set up a confidence threshold. Let's define it to 0.35. You can change it to a different value. Let's start with this value. This will be the minimum value for the prediction. We then use our model to predict the bounding boxes on this image. We will do this within a torch no grad function context to disable gradient calculation, as we're only doing inference. And after that, we will create another variable named outputs, and this will contain all the prediction results of our model. So now we have an outputs variable that contains all the predictions, and we have to do some conversions of the information from types of a tensor in order to extract the image out of these results. So we do a post-process using the image processor, and this converts the raw outputs into a format that we can easily use. And we also apply our confidence threshold during this process. And the last phase is basically creating our output image. So in order to do that and visualize the result, we convert the process results into a detection object from the Supervision library, and we create labels for each detection, including the class name and the confidence score. The last phase is creating our image within the detections. So we are using the box annotator class that includes the annotate function. We are sending our image and the detections and the labels to this function, and the result will be an image with all the bounding box and the detected objects. And let's display our image and see the result. Let's run it. Let's wait a few more seconds. Great. So we have on the right side the original image, and on the left side we have a bone fracture named line. Let's try it with another image. Let's choose another image. Let's choose this image from the test data, and let's run again the inference process, and we have a different image with a different fracture. Great. I hope you enjoyed this tutorial. Thank you very much. Bye bye.